So in this video, we want to look at what if we're compounding continuously, and this is going to change our formula a bit. So with compounding, in general, we would use that formula that we just looked at, where n is representing the number of times per year it compounds. And what we're going to do in this video is see what if it's compounding all of the time. And this might sound like then you're just making infinite money, like, yeah, always choose compounding continuously. But it actually behaves a little differently than that. So first, before we get to the formula for this, I want to talk about what E is. So E is a number that comes up in mathematics. And with that, I just want us to have a little background of where it comes from. At no point will you be tested or asked to recreate this, just so that we're not throwing a new idea at you without not really having a background for it. So something that's part of calculating E is thinking about what happens when we take 1 to a power of 5, or 1 to a power of 10, or 1 to a power of 3,892. I think if you take 1 and raise it to a power, it's always 1. Doesn't matter what exponent you put on there as long as it's positive. If it's positive, you're getting 1 out. So that's going to be an idea that we'll come back to in this. This table here is something you could fill in with your calculator if you want to try it out for yourself. But it's the idea of having these different values for n here and plugging into this equation. So like this first column here, I'll fill out this column of 1 divided by, and it's that we're plugging in 1, or 10, or 100, or 1,000. So we're creating these fractions here. So 1 divided by 1 is just 1. 1 divided by 10 is a 0.1. Then we'd have a 0.01. 0.001, 0.0001. So as we're plugging in larger and larger things into the denominator here, we're getting something very small, like 0.00001. This is extremely close to 0. So I'm going to just write a little summary of what this represents as we go down these values for n. It's that it's just a little more than 1. So what if we take the value from this column and add it to 1? So that's what the second column's asking to do. Take our 1 over n values that we just found here and add 1 to it. So like here would be 1 plus 1, which is 2, 1 plus 0.1, 1 plus 0.01, so on and so forth. So we can just see how this turns into where before was just a little more than, I'm sorry, that should have said 0. Now this is something that's just a little more than 1. So this 1.00, and sorry, I'm writing too quickly right now, apparently. Well, there we go. Another 0 in there. This is just ever so slightly more than 1. So then here, what we're going to add on is an exponent. You can imagine as we go down the line here, we're taking something that's just a little more than 1, and then we're raising it to these really big exponents, to the point where at the end here, we'll have an exponent of 100,000. So 2 here, it's going to be simple. 2 with an exponent of 1 is just 2. And then this would be a 2.59374. This would be with that exponent of 100. So we're taking that 1.01, raising it to an exponent of 100. So that would be a 2.70481. This would be a 2.71692. This will be a 2.71814. And this last scenario here, which this really gets at the general idea of what we're looking at, is what if we're taking something that is ever so slightly larger than 1 and raising it to the 100,000 power. Because if it was just 1, like if we just used the rounded value and took 1 and then put an exponent of 100,000, we know what happens then. What we want to understand is what happens if we just put a little teeny tiny bit more on and then raise it to this huge exponent. And what the calculator will give you is a 2.71827. So this whole idea here is what if we just take a little bit more than 1, and then raise it to a really big exponent. And I'll go as far as putting infinity there. And what you can see is we get something that would round to 3, but this 2.718. If you go to your calculator and find a button for e, and often with calculators it'll ask for an exponent, so you could just plug in a 1 to get the actual value of e. What your calculator will give you is a 2.71828, and so on and so forth. It has a long decimal at the end. That's where this number e comes from. It's this idea that, okay, raising 1 to a large power is just 1, but if we put a little teeny tiny bit more onto 1 and then put a large exponent, it converges, it approaches this value right here coming out from our calculator. So e, this is named after a mathematician, or rather he named it after himself. So this is Euler's number. And that's why they use the letter E with it. And that's why when we choose variables for word problems, we usually avoid E, and it's because it's a number. If you see the letter E coming up in mathematics, it can be replaced by this number right here. So it's just a number. It's an irrational number, meaning it has decimals following that never repeat. There isn't a fraction that can substitute what those decimals are doing. And this is very similar to what we see with pi, where pi, it's a symbol, but really we could replace that with the number 3.14159. It's an irrational number where the decimals just keep going afterwards without any sort of pattern to them. Similar idea with Euler's number. So when you see this letter E coming up, you just need to keep in mind that it's a number. It's about 3 is what it would round to. So when we compound continuously, with our original formula, we had our principal, 1 plus r over n raised to the n to the t. And what we're doing, and how this Euler's number comes through, is that where we have n to compound continuously, so all the time, is thinking about putting this really large number where n is, and putting this really large number where n is, which is very similar to what we just saw in the formula up above there. We have that rate, but it's this piece that's coming through with what we calculated up above, having 1 plus a little bit more, if we just kind of ignore the rate for right now, with a really large exponent. How that behaves is it turns into e. So our formula for compounding continuously, to find the balance of the account, we'll take our principal, so that isn't part of it, but then this kind of yellow part that I highlighted here can be replaced by e. And then in the exponent, that's where our rate will come in. So we'll have our rate times time for the number of years. So that's our formula when you see compounded continuously. E, I'll show you on our Desmos calculator of where you can find that. Most calculators have a button for it, or at least scientific calculators, so we can plug it in. Another piece here, if we need effective rate, so if we were just interested in the percentage growth, that calculation would go taking e raised to the power of the rate and then minus 1. So let's try this out. With this first example here, let's see, you get an inheritance of $15,000 and you put it into an account. So that's our initial deposit. So there's our principal. It pays 7.1% interest. And what we want to notice is that it says compounded continuously. And something I like to do when I teach this class is whenever you see compounded continuously, I always just write E right there. When you see compounded continuously, E is going to be part of the formula. So because they say compounded continuously, we'll have E, and then how much will this be worth in 25 years? So to find the balance of the account, we'll take our principal. We'll have E as the base of the exponent, and then in the exponent we'll have the rate times time. So let's see how to plug this into the calculator. And then we'll have E. Now you can either use E on your keyboard, so like I could type E with the keyboard and then for my exponent go there, or at least with the Desmos calculator, if you go to function, you can see this e to the x, you can grab that. Either one will work. Typing an e from the keyboard, it'll know to use the math value of e. So, and then just like our exponent before, we'll need parentheses here. So 0.071 times 25. And then close parentheses, and we'll have this $88,504.22 is how that will round. So this will be $88,504.22. All right, example 2 here. We're going to invest $1,000 for 5 years, and we're going to have 2 options, and we want to see which one's better. So we have this APR of 5% compounded annually. So with that, the formula we'd be using is that principal 1 plus r to the t. You could use that compounding formula with n, it's just n would equal 1, but it would be the same thing. And then continuously is going to be e, so we'll have equals p times e to the rt with this rate of 4.7%. So again, this idea of compounding continuously is generally better because the more it compounds, the more money you're making, but they're giving you a lower percentage rate, so it's hard to tell. So there's 2 ways we can do this. We could do this with effective rate. Effective rate's great for comparing accounts to each other. So if we compare account A and B in this scenario, so with account A, we'd be taking that one, well, it's an annual rate, so we actually don't need to calculate anything for account A. It's just going to be that 5% for the effective rate. But then for account B, since it's compounding more than annually, we'll want to take e raised to the power of the rate of 0.047 and then take 1 away, and that would be a 0.0481, so 4.81%, which is lower, so this account A is better. So that's one way we could have done this. Another way is they did give you a principal, so you could just figure out how much you would have after 5 years. So you could use the balance of the account. So if we did 1,000 times 1 plus the rate to our exponent of 5, we'd see we'd end up with $1,276.28. Or with account B, for the amount we'd have our principal times e with a power of 0.047 times the amount of time, which is 5. And with that, we'd end up with a balance of $1,264.91, which is still lower. So because they gave you a principal, either method's great for comparing the accounts. The effective rate will always work, so if they don't give you a principal or amount of time, you'll want to use that effective rate to solve. And then just one more example here. So how much would you need to deposit in an account that pays 5.25%? So there's our rate. And it's compounded continuously, so we're using E. And we want to have $20,000 in 20 years. So they're asking how much would you need to deposit? They're asking you, what is the principal? This is the first time we've seen one of these problems in these videos where it's kind of switching what it's asking for, but basically it's telling you the balance that you want to have. So how much would you need to deposit now to have this balance in 20 years? So we're going to use our formula, and we'll plug in just as we do, it's just what we solve for is going to change. So this would be 20,000 equals P E, and then our rate is 0.0525 times time of 20 years. So what we're going to want to do is to solve this, what we need to do is simplify. And what we can do is plug all of this right here into the calculator to get a value. Or if you're comfortable with it, it's that we're dividing both sides by this value of E. So either way, but if it helps, you could simplify just to get a number on that side. So let me go ahead and show you this with Desmos. I'll move to a different problem here. So we're going to have e with an exponent, and then that 0.0525 times 20. So you'd have this rounded value. Of course, with these problems, and in general with these financial math problems, rounding even to 4 decimal places can really throw off the answer. What's nice about these online calculators is you can copy and paste as you would like. So I'm going to go ahead and write it down as somewhat rounded here, but I'll show you how to get the exact answer out from the online calculator. Because once we get this, we can see what we want to do is divide both sides by that number. So to get my value for P, what I'm going to do is take 20,000 divided by that value. So in my online calculator, what I can do is I'm taking 20,000 divided by, and if you want the answer, if we want to repeat this answer right here without having to type it all out, which isn't the worst thing, you could just start typing and just include as many values as you can. But to get the exact answer copied, there's this answer button right here. So if we click that, it's just going to copy and paste for you, and then we can get this exact answer out without having any rounding to create any error. So our final answer there should be $6,998.75. So that's our compounding continuously function.